Okay, great. Thanks everyone for coming. This talk is about few-shot symbolic learning. So what exactly do I mean? Well, I was spending some time this week in the National Orchid Garden, not far from here. It's fabulous. I recommend it to you if you haven't been. I'm not much of an orchid expert, but I was looking at these flowers and wondering, how do you identify them, right? So many different colors of orchids, right? I thought there were 5 petals. It looks like there's a fancy lip in the middle. The petals seem fairly thickish. So what could be useful for the identification of orchids? Is it the color? Is it the size, the shape, the number of petals, how big the plant is? So which features are relevant and which are irrelevant for identification of flowers? So I was asking about identifying a flower domain. Right? I knew very little. I guess after reading, I realized there's actually 3 petals and 3 sepals. The middle lip is itself a petal, right? So not knowing anything about this flower domain and only having seen a few orchids, could I classify some other ones that looked somewhat different, right? So the ones on the right are also orchids. They have these, the red one has these thin petals and the purple one's got these fat, plump ones, right? So the idea is that to do this kind of few-shot symbolic learning, classifying things in terms of their features, I had to understand something about the domain first. There's simply too many features to consider as a newcomer, right? And learning the domain should somehow permit learning concepts from few examples, right? I think this is kind of pervasive, right? And people tell me in bird identification, it's sort of similar. There's all these things that you learn to look for on the bird to classify them, right? I think it's similar also in other domains of learning, so understanding mathematical structures like graphs, right? You first figure out what are the relevant questions. There's nodes and edges, and people care a lot about connectivity. And then seeing a few examples of more exotic graphs, you're more prepared to quickly learn them. This also comes up in programming languages and verification, so trying to learn programs from few examples, the classic case being spreadsheet automation in Excel, so you have a few input-output examples. You're trying to learn a program that somehow captures a user's intent and can help automate filling in the spreadsheet. Or you're trying to prove programs correct, and you need to find these inductive invariants, and you can treat this hard problem as a learning problem. I'm going to learn a logic formula that expresses the invariant from states of a protocol, so sample behaviors of programs. Right? In all of these cases, the challenge is often to understand the domain well enough to write down a DSL which captures the common concepts and computations for that domain. And then often people have designed, synthesis algorithms specifically to those DSLs, right? But typically, I think the step 2, designing the DSL, is done with an eye toward 3, right? So how can we come up with a DSL so that some kind of few-shot synthesis algorithm is likely to succeed? So this is the step we're interested in here. So one way DSLs can make this feasible, few-shot learning, right, is to express relevant things succinctly. Another thing they can do is express irrelevant things less succinctly, or perhaps not at all, right? So if we take the spreadsheet domain, many programs are going to do things like, split strings on white space and capitalize things and manipulate dates and times and formats like that. But they're unlikely to do ASCII character code arithmetic, right? So a good DSL for spreadsheets will exclude that. Right? The more general observation is that DSLs, or useful DSLs, are often less expressive than general purpose languages. This is the kind of abstract setup we're considering, right? So given just a few examples, some learner has to produce a hypothesis in a symbolic language, a DSL, that's consistent with the examples, except we don't have the DSL here. So the goal is somehow automatically construct a DSL so that this particular class of learners biased towards simplicity are likely to succeed from few examples. The first contribution of this work is a new formulation of DSL learning, or DSL synthesis, itself as a learning problem. So what do I mean? Suppose we have a few-shot learning instance, just a few input-output examples on integer lists, and we have a fixed DSL programming language, and we're going to take a very simple algorithm that just enumerates small expressions and increases the size as needed, enumerating programs until it finds one consistent with the examples. Okay, so here it found concatenating the input list with itself, right? That's consistent with those two examples, right? But now imagine that I held out a testing example on which the concatenation program is not correct, right? But perhaps if we had looked for a slightly bigger program, we would have found this one, the stutter program, which is just repeating each element of the list once. So that would have been consistent with the training and the testing examples. But we didn't find it because we were using an algorithm that was going to pick the simplest program, right? So one could blame the algorithm, or one could blame the language here, and we're going to blame the DSL. So we're going to say we like the algorithm that picks simple concepts, and we're going to try to get a new DSL that can solve these problems. So the idea is to take these learning instances, split into training and testing sets of examples, and treat them as a kind of DSL learning example. So the learner knows that it's going to be tested like this, and it gets to see the training and the testing examples. Okay, just to formulate the problem more precisely, the learner, the DSL learner, gets multiple of these few-shot learning instances, and its goal is to somehow construct a DSL that maps these, maps some concepts sort of higher up in the DSL in the sense that they require more complicated expressions to express, and the solutions, the expressions that solve both the training and the testing examples should be expressed more succinctly relative to those concepts. And another feature of this formulation is that the DSL can choose not to express some concepts at all, right? So whatever mechanism we're using to define the DSL, we might end up with one which is less expressive than we started with. So this is just a precise problem formulation. We fix some base language L, and a notion of complexity of expressions in the language L. And we're given a set of few-shot learning instances, as described, and then also some kind of metagrammar, which is specifying the space of possible DSLs. And the goal is then to synthesize a grammar in that space that contains some solution for each one of these learning instances, which is also somehow minimally complex among all the expressions that solve the training sets of examples. This is just formalizing the intuition from previous slides. So as an example, imagine you had a language of, you're trying to classify points in the plane, and your language consists of some primitives which are specifying rectangular regions of the plane, and you have maybe many of these regions at your disposal, but finitely many. And you're trying to cover some positive points and exclude negative points. And imagine the training examples are positive points and the negative examples are testing points. And what you see here is that for this language, it's not suitable for this learning instance because it expresses a very small disjunct, which covers the positives but doesn't exclude the negatives. Whereas a larger conjunction with 3 terms does capture the data set, but it's larger, right? So the idea is a DSL, in this particular case, should favor conjunction over disjunction. Okay, the second contribution is a set of decidability results for this problem. So what is decidability here? Remember, we're given some learning instances as input and some description of the space of possible DSLs. And decidability is trying to answer the question, does there even exist a DSL in this space which has these properties, right? So can we synthesize one if it does exist and also terminate and say, no, no such DSL exists? So that's decidability. We have a theorem which says that DSL learning is decidable when the complexity measure is parse tree depth. And this is actually a meta theorem. It holds over any base language with a finite aspect evaluator. So we get as corollaries concrete DSL learning results. Now this finite aspect evaluator thing, this is referring to some prior work of ours, showing that a large class of languages admits decidable learning. So we have decidable DSL learning results for any of these base languages, including first-order logic with recursion. just a brief sketch of the proof idea. We have these learning instances, and we have to decide, is there any DSL at all that could work? Right? So what we do is we design a tree automaton, that's A, which reads a tree that encodes a DSL, and it traverses this tree up and down many times to check these conditions. It says, does there exist some sufficiently succinct solution? Okay. And eventually it outputs yes or no, and hopefully it only says yes on the DSLs that have these properties, and it says no on the ones that don't. Once we have A in hand, the decision problem for DSL learning reduces to tree automaton emptiness with some standard techniques. Okay, there's more in the paper, including some variants of this problem and decidability results for those. In particular, we looked at a natural weakening of the problem, which we called adequate DSL learning. So this is the version where we don't have these test sets, and we just have a bunch of examples as a learning instance, and we're trying to make sure that our DSL expresses a solution for each of them. We also looked at varying the mechanism by which you define DSLs. So instead of using grammars, we can use something slightly more expressive, a macro grammar. So this is a grammar that has non-terminals which can take parameters. There were also some unresolved theoretical questions. In particular, are these problems decidable when the complexity measure is parse tree size? So we have results for depth, but is it decidable for size? We don't know. Future work will be to find an efficient algorithm and implement it. So this is the decision procedure here is very complex. I think an interesting question is, can useful DSLs be learned from this specification? And if so, how much data do you need, right? Okay, so that's it. This is I think, a very interesting new formulation of DSL learning, which is about precisely identifying a domain for the purpose of few-shot learning. And it introduces a kind of signal related to inexpressivity and succinctness, where solutions to learning problems should be relatively more succinct to tempting non-solutions. And we proved decidability for a rich class of base languages. That's all.
Hi, cool topic. Are you familiar with ADF, automatic defined functions?
No.
In the world of genetic programming. So it's very similar to the DSL learning. They just, instead of using, well, they also use grammars, but their DSL is a subset of functions that can include new functions that are defined based on the basic elements. So I think your work should also apply to that area. And the part I want to ask you about is, do you know the ARC prize, the automated reasoning corpus?
Yes.
So would this work given enough computational time?
Yeah, this was actually partly kind of in spirit motivated a little bit by thinking about ARC, right? So you have in ARC these abstract reasoning puzzles, few-shot learning puzzles, but there's no formalized DSL. So there was a question of maybe one should discover the DSL for ARC. And I think this problem, you know, if you could solve it, it would be interesting to see. You know, run it on the publicly available ARC puzzles and obtain a DSL and then try to solve with that.
We should talk as there's a DSL available, but there's also the challenge of discovering it.
Yeah.
One more really quick question while Anna's getting set up.
Okay. Yeah, I'm wondering why do you define this in fusion learning? It seems that your problem definition is quite general and applicable to any DSL learning scenarios.
I'm sorry, I missed the first part.
Why do you add this fusion learning scenario in your title of your paper?
Why few-shot learning?
Why fusion learning?
Yeah, I think you know, if you have a lot of data and you want to learn something, you know, it seems more in the
domain. I mean, your approach seems to be more general than fusion learning, right? It's general DSL learning.
Yeah, well, I think the problem of identifying the domain is really a problem for few-shot learning. So you want to do learning from few examples. How can you possibly do that? without somehow constraining the space, right? So,
Okay.
yeah.
Yeah. Thank you.
All right, let's thank the speaker again.